Good morning, everyone. Thank you for joining today's webinar, where we're going to discuss improving sample analysis using combined energy-dispersive and cathodoluminescence spectroscopies. I'll be your host, Jonathan Lee. I'm an application scientist with Gatan, where I specialize in using our CL products and demonstrating our Monarch CL detector. I'm joined by Timmons Erickson of Jacobs Jets Astromaterials. Timmons is a research scientist within the Astromaterials Research and Exploration Science Division at NASA Johnson Space Center. He primarily works on textural, chemical, and microstructural analysis of impactites, meteorites, and planetary materials, linking microstructures and textures with isotopic or geochronologic analyses to try and date ancient events in the solar system and here on Earth. So welcome, Timmons.
Thank you, Jonathan.
Good to have you. So attendees, if during the webinar you find that you have questions, please submit them in the questions pane. Issues regarding connectivity will be addressed as soon as possible, and questions for the speaker will be answered after the presentation. So let's just talk first about instrumentation and the experimental techniques that we use. First was energy-dispersive spectroscopy, where when an electron beam strikes a material, a ton of events are kind of stimulated there, including secondary electrons, backscattered electrons, and these events can kind of reveal different properties about the material that you're investigating, including high energy photons or X-rays that reveal compositional analysis through energy-dispersive spectroscopy. And we do that just by attaching an EDS detector onto the side of our microscope chamber, and in this case we used an EDAX Octane Elite EDS detector. We typically get a detection limit down to about 0.1 weight% of the material that we're investigating. All right, and here's an image of the electromagnetic spectrum, where for EDS we typically get something in the X-rays from 10 to 19 to 10 to 17 hertz frequency. So looking back at the many processes that are stimulated in the specimen when struck by an electron beam, the other that we're going to investigate today is cathodoluminescence, which is just a light that's emitted from the specimen. It can reveal more information about the band gap in the material. We do this by bolting on a cathodoluminescence detector and analyzer. We extend a parabolic collection mirror above the sample, and we couple the light back into the detector that way. This allows us to correlate optical, chemical, and structural properties down to the nanoscale. We can couple these two techniques together, which they give a lot of supplementary information to one another. We do that by, again, we place a paraboloidal mirror above the sample, which typically would block out the line of sight that you would need to the EDS detector, where in this case we've developed a collection optic which allows a line of sight from the specimen to the EDS detector, as well as coupling a significant amount of the light sent from the sample back into the CL detector. So the electron beam passes through an aperture in the paraboloidal mirror, strikes the paraboloidal mirror, and then is coupled back into the CL detector. But also there's a cutout that allows the X-rays to reach the EDS detector. And so using these two techniques together, we kind of get complementary information about the specimen. The specimen in this case is a meteoritic specimen that I'm going to let Timmons introduce. All right, so let me just give it control.
All right, thank you. Yeah, so today we're going to be talking about a CO3 carbonaceous chondrite, Miller range 090010, which is a mouthful, but it was a 2.5 kilogram stone that was collected during the 2009 Antarctic Search for Meteorites field season. As mentioned, it's a CO3 carbonaceous chondrite. That means that it's C, carbonaceous, and an Ornan style, and 3, moderately to low shock pressures. On the exterior of the grain, we see a black fusion crust. This is generally glassy, but where it's been broken away, we can see a dark rusty brown interior. And the interior has a lot of fine-grained white inclusions. In this section, we can see that it's composed of lots of chondrules, which range up to about 1.3 millimeters in size. And there are also abundant calcium aluminum rich inclusions, or CAIs. These CAIs are very fine-grained. This is a petrographic light microscope image of one with the cross-polarized and template in. So why are we interested in CAIs right now, carbonaceous meteorites right now? Well, they're the most primitive meteorites that fall to Earth, and as their name implies, they're rich in carbon. And so they are believed to have been potentially the building blocks for life on Earth. There are also genetic links between CO and carbonaceous chondrites with primitive asteroids, such as Bennu and Ryugu, two of the Apollo family asteroids that currently have ongoing sample return missions. The JAXA-led Hayabusa 2 mission recently returned material from Ryugu, while the OSIRIS-REx mission, led by NASA, just left Bennu and is expected to return in late 2023. In the meantime, studying these carbonaceous chondrites will guide future investigation of these return samples and help us refine the techniques we'll use. This is just, I think, a kind of exciting image of the OREX sampling. And the collector itself was actually so filled that they couldn't originally close it before they locked it down into the capsule. So we're expecting to return a lot of material from Bennu. So, chondrules and CAIs. Well, chondritic meteorites are composed of these two components. Chondrules themselves make up the dominant material, whereas the calcium aluminum inclusions are less common. Chondrules formed from these distinctive molten droplets. They're believed to have formed either in the solar nebula or in impact processes on the early asteroids that formed. And they typically are composed of phosphoritic or magnesium-rich olivine. Calcium aluminum inclusions formed even earlier than chondrules. They're dated to 4.567 billion years ago based on their lead isotopes. And they are composed of highly refractory mineral phases, and even including corundum, and then other materials such as grossite, spinel, perovskite, himonite, and melite, which are thermodynamically calculated to have condensed from the gas, the nebular gas. These materials, CAIs and chondrules, represent the building blocks of asteroids, planetesimals, and ultimately the planets. Therefore, understanding their complex history of formation and any subsequent reworking is critical to resolving the early planet formation history. Typically, CAI textures are characterized using backscatter electron imaging and energy-dispersive spectrometry. Chemical maps, their growth patterns reflect their formation in the early solar system and then subsequent alteration and transportation through the stellar environment. We're going to focus on this CAI, this calcium aluminum inclusion from MIL 090010, CO3 carbonaceous chondrite, and it's composed of spinel, himonite, melite, and calcipyroxene with minor anorthite and perovskite. Cathodoluminescence imaging reveals subtle zonation patterns that reflect this complicated crystallization and alteration sequence. And coupling EDS and CL really give us in-depth view of that history of this grain, which can't be resolved with solely one technique. So I'm going to hand it back over to Jonathan who's going to tell you more about how that data was collected and the post-processing that he did. So Jonathan, take it away.
Thanks, Timmons. So first, let's look at the EDS data. So this is the secondary electron image captured from the specimen. We can take a look at the EDS spectrum image. This is displaying a bandwidth around the oxygen line. We can take a look at just a few EDS spectra around the surface of the sample. And you can see there's a lot going on compositionally. So in order to get an idea of what's going on a little bit more in detail across the sample surface, we mapped out the EDS data across the sample surface. So this is an EDS spectrum image where we've mapped out the aluminum, the calcium, and the magnesium in the sample. And then if we stack those up into an image, you can kind of see where those elements are and in what quantity. So you can see where there's regions there's calcium dominant, there's aluminum dominant regions, and then there's magnesium dominant regions as well. But you'll notice also that it typically doesn't give you a lot of nuanced information. You can see different shades of blue, but only really like 2 shades of blue. And the same with green. You only see a few shades of green. So you run into an issue of the nuance and subtlety that's definitely present in the sample, for which we took a look at the CL, or the cathodoluminescence, in a co-acquired spectrum image. So this was acquired at the same time as the EDS spectrum image. And again, we can look at the spectra from the same point. So these are cathodoluminescence spectra from spots 1, 2, and 3. And immediately we recognized that some of the spectra were unique to given materials. So for instance, spinel has a very characteristic CL emission spectrum related to, I believe it's chromium additives in the crystal. But it gave us a starting point to identify unique spectra across the sample surface and use a multilinear least square fitting in order to find where are those materials and in what quantity across the sample surface. And so one of the materials we found, again, was calcic pyroxene, and this is the map corresponding to that. You can see the pyroxene tends to kind of coat or shell every or the other materials. So looking again, we found actually 2 phases of melolite. So a melolite kind of is kind of pushed up against the calcic pyroxene, and then the hibonite grains, which tend to form the cores in the northern part of the specimen, and spinel. So spinel has probably the most easily identified CL spectrum, but you'll notice also that it has lesser influence towards the north part of the specimen, and it's more dominant in the southern part. And so then we can actually identify across the sample surface and then stack those up as well. So you can see the spinel, the hibonite, the melolite, and the pyroxene across the sample. And so now we've taken our elemental quantification and used that to verify the CL spectrum that we're using to identify the minerals in the specimen. We also noticed that not all melolite grains are created equal, as it seems. And so if we look at just a small grain right here, this hibonite grain that's in maroon, we grab spectra from points 1 and 2, and we can look at both the EDS and the CL spectrum. And we can see that compositionally, those 2 points turn out to be nearly equivalent. There's almost no discernible difference between the 2. And then the CL spectrum, however, has a noticeable peak at 460 coming from spot 1. So at around 460 nanometers, there's something going on there. And so then in an effort to map out where is the influence of that peak and what is it doing, I performed a difference method. So I looked at where that peak is and took a difference with the background of the surrounding area, and then in order to kind of eliminate the influence of the background, so we can really just see where that peak is. And it turns out that it's most prevalent towards the interior of the grains of the hibonite. And it turned out there's another peak as well, around 606 nanometers, which tend to be more prevalent out in the melolite and pyroxene regions. All right, so if we go back to the material identification image, and then we'll go back to the broader image and show what it looks like whenever we map, again, those trace elements across the sample surface. Right, and you can see there's a lot of influence. It tends to vary across the sample surface. And we identify those materials to be samarium inclusions in melolite and iron in the hibonite material. And just for a sanity check, just to make sure that we're able to actually pick up iron, here's the EDS iron map. And you can see we're going to pull a spectrum from this point where we have a high influence of iron, and over here where we have supposedly very little. But that's because in that material, iron's not, or rather that's not melolite over here. So we're just really just proving that we can detect iron in some abundance. And so we can, and then we can look at over here in the hibonite where we're expecting there to be some iron, and it turns out we don't detect any. And so we conclude from this that the CL spectrum image is in fact detecting trace elements, because we know CL can be affected by much lower concentrations of elements that are included in them. So, you know, we're detecting on the order of parts per million in CL, and so then we can look at spectra from two regions of hibonite and see again the EDS spectrum nearly match. They're almost completely identical, whereas the CL spectrum tend to vary, especially around 460, where you can see the influence of a large peak at spot 2. CL also gives us the opportunity to look at grain boundaries. So this is something that you don't get from EDS, where in EDS we have a high confidence of elemental quantification and element identification, but in CL you have the opportunity to see more nuanced information like grain boundaries. As you can see here, we're seeing some brights here in the middle of this grain of hibonite. If we look at the true color CL image, so this is just the same image but converted to true color, you could see again more subtlety in the melolite regions, where you see a higher intensity of blue towards the outer edge of that melolite. But again, in the EDS image, we don't see really much or any variation in the surface there that would suggest that we would see any of that we see in CL. And I'll hand it back to Timmons to explain what that means.
Thank you, Jonathan. So, as Jonathan mentioned, we seem to see two domains in the CAI, one that's more spinel-rich and one that's hibonite-rich. And so the hibonite-rich domains appear to have crystallized individual grains of hibonite, whereas down in the spinel-rich domain, we have intergrowths of hibonite, spinel, and even some minor grossite. The interesting thing is that it appears not getting the next slide. There we go, sorry. There seems to be a control based on that primary crystallization on the microstructures that form. We see the development of sector zoning in the hibonite consistent with some thermal alteration or metamorphism, and subsequent alteration overprinting the hibonite grains. This is all mantled by melolite, and actually what's interesting is that the melolite compositions, that melolite 1 and 2 that Jonathan was showing, appear to be related to the primary grains, are the hibonite versus the spinel-rich intergrowths, their chemical compositions. And further to that, in the southern domain, we do see minor anorthite that is crystallized, mantling the melolite, and it's lacking from that northern domain. again suggesting that primary chemistry controlled the phases that were the alteration products that resulted. However, all of this material is mantled by a thin layer of calcic pyroxene. And so combining these two techniques, we not only get information about the crystallization or the growth sequence and the alteration of those different phases, but we can also see subtle zonation patterns and grain boundaries that would not be evident by just using one technique. So in summary, energy-dispersive spectrometry accurately and quantifiably detects and identifies elemental species constituents in a specimen. However, defects, grain boundaries, and trace elements are not observed using this technique. Cathodoluminescence reveals the local charge recombination properties and is thus, sorry, not getting the rest, but it's sent, there we go, a little delay, a little lag, sorry about that, folks. And therefore, the grain boundaries slightly alter the recombination dynamics detectable by CL, and therefore we can use this to identify different grain boundary and textural techniques. The material can be identified through emission spectrum. So specific phases such as spinel have unique CL signatures that can be used to identify those phases. And trace elements can be determined at ultra low concentrations, much lower than what is detectable using EDS. Combining these two techniques, EDS and cathodoluminescence spectral imaging, can reduce sample dosage, simplify the workflow, and offer this correlated perfect pixel correlation, and therefore is a very strong technique for identifying complex zonation patterns in crystallization sequences in things like these calcium aluminum inclusions, which have had a significant and protracted history in the early solar system. I think we're going to open it up for questions now. I'll turn it back over to you, Jonathan.
Thank you, Timmons. All right, so as I said, if you have questions at this time, please submit them in the questions panel. We have a few questions coming in. All right, this one's for Timmons. Why did we choose this CAI to analyze?
Thanks, Jonathan. Well, we originally chose this CAI and a handful of others because we thought they may contain corundum inclusions. And although this particular CAI didn't contain any corundum, the complex array of textural domains, intergrowths, and overprinting that was identifiable, I think, really highlights the efficacy of using this combined CL-EDS approach.
Mm-hmm. Yeah, I agree. It was really effective. And then I have a question here. What is the trace element detection limit? So for CL, it really just kind of depends on the material and what the, what sort of additional elements are in there. But, it's not atypical to find the detection limit for CL down in the parts per million range. Right, and here's another question. What do we intend to use the data for, and what do we plan to do next on the sample?
I can take that one. So the data we'll be using to guide subsequent or future analyses, such as looking at nanoscale features of these growth domains using transmission electron microscopy, And it can also be used to guide future stable isotopes such as oxygen isotopes or radiogenic isotopes such as aluminum magnesium dating analyses. And this will all help us further understand the formation history of this grain and trying to link that to its where it formed in the solar nebula and what kind of the different domains reflect. So I'll leave that back to you, Jonathan.
Sure. Thank you. All right. And another question is, what were the settings to collect CL data? So the dwell time per pixel was something like 0.1 seconds, 375 by 375 pixels. So the beam was around 10 kV, I think, and I think that's it. So the lateral resolution that we can typically achieve using a 10 kV beam in those materials is on the order of 30-40 nanometers. So we didn't really lose anything to spatial resolution to the beam spot size or the generation volume in that regard. We'll do one more question. So regarding CL analysis, does it have a library to further check on the phase structure of materials, or is there any standard material for verification? So right now, the answer is not yet. We're actually actively building a library of CL spectra so that when researchers find something, they can rely on that in order to identify those materials and what phase or condition that they're in. All right, I'd like to thank everyone for their questions at this time. We'll be following up with you guys offline. So I'll submit responses to your questions, Timmons or myself, within the next 7 business days. Thank you all for attending. The recording will be posted to our Gatan.com website in the next few days. So if you have any more questions, please submit them either to myself or to the questions panel. And if there's nothing else, Timmons, thank you for attending, or thank you for presenting with me, and thanks everyone for attending.
Thanks, Jonathan. I appreciated this.
All right. All right, thanks everyone. Have a great day.